All right, what's going on, everybody? Today we're doing another LeetCode video. This one's called Construct Binary Tree from Preorder and Inorder Traversal. So we're given two integer arrays called Preorder and Inorder, and they want us to construct a binary tree from those two arrays. Now, both of those arrays are going to be corresponding to the same tree they want us to construct. All the values are going to be unique. So really, the challenge here is finding a way to basically map the in-order array onto the pre-order array to determine how we should actually, construct the tree algorithmically. So I think a good place to start here is just making sure we understand exactly what a preorder and inorder traversal are. So a preorder traversal is basically going to be, the pattern for preorder is going to be root, left, right. So, and then the pattern for inorder is going to be left, root, right, recursively. So let's actually build the tree and look at that. So for preorder, if we follow this pattern, root, left, right, I mean, you can't just build the tree from one of these arrays, because it's like, okay, we obviously know the root is going to be here, but we don't really know where left ends and where right begins, right? So, but I'm using the same example from the problem, so I already saw it. So the root here is going to be that 3, and then the left subtree is just going to be the 9. And then the right, we have a 20. It's the same pattern again, recursively. So the root here is going to be the 20. The left subtree is 15. And then the right subtree is 7. So that's the preorder traversal. And then similarly for the inorder traversal, we have left, root, and then right. So the left, we would start at that 9, right? And then there's the root, right? And then there's the right subtree, but it's recursive, right? So the 15 comes first because it's left, root, which is 20, and then right, so the 7. So that's kind of the idea there. I mean, I think it's a little easier almost to go backwards. I mean, it literally is easier to look at this the other way, right? So looking at the trees first, right? So the preorder traversal, if you just go around the tree, that might be a little confusing to use that color, but if we just went around the tree like this, that's an easy way to visualize a preorder traversal. So you start at the root, then you go left, and then you go right. So we can see that that's the correct order. See 3, 9, 20, 15, 7, right? So that's the right order for preorder. And then for inorder, it's the same idea, but you have the left subtree first, right? So this 9 comes first, and you have the root, and then you have the right subtree, but it's recursive. So you have the left first, then the 20 for the root, and then the right subtree. So pretty similar. So that's it for preorder and inorder traversals. So we can kind of use that to our advantage. So in our algorithm, we're basically going to have some pointers, right? We'll have a left pointer here, and then a right pointer here for the preorder array. And then we're going to do the same thing for the inorder array. And so kind of the strategy here is like, and let me just erase this. So we're going to start with the preorder array, right? Because we know that this is the root, like for sure, this 3 is going to be the root. So we could add that to our tree, right? Add that 3 to our tree. Okay, but then it's like, what do you add next, right? We can't just use this preorder array alone. We're going to use this inorder array to help us, because once we've used this 3, it's like in the preorder array, we already said, like we know the left subtree is going to be over here somewhere, and the right subtree is going to be over here somewhere, but it's like, where's the left end? Where's the right begin? Well, exactly where this in-order array splits it, right? We can see the left subtree is for sure going to be right here. It's this 9. So now we know exactly what it is, and we can basically just map these two arrays onto one another. But we're going to have to do some a little bit of fancy arithmetic when we're passing in our pointers to our recursive function calls. So let's go ahead and derive some rules for that. And this is really the challenge, I feel like, of this problem. So let's do that. So let's make some rules. So we need some rules for building a left subtree and some rules for building a right subtree, just for these pointers, right? So left, right. So the red is going to be for the preorder array markers, and then the green will be for our in-order array markers. So let's get the easy stuff out of the way first. So it's pretty straightforward to update the left pointers for the left subtree and then the right pointers for the right subtree, because as you can see, like if we were to use this 3, we can tell that, you know, obviously our left subtree, or the left subtree in the preorder array is going to start 1 over every time because the root comes first, right? So we literally just need to add 1 to whatever that left index was before. And then for the in-order, it can just stay the same because it's left, root, right instead of root, left, right. So this will literally just stay the same. And then for the right markers for the right subtree recursion, the right index is always going to stay the same. And for the preorder and for the in-order, because they both end in the right subtree, right? So these are going to be the same. They're not going to change. So it's a little trickier now to figure out where the right ends, right, and where the left begins. But the way we're going to do that is we're going to have an additional variable that we'll just call alpha here in the whiteboarding, and I'll call it like offset or something in the code, but we'll just call it alpha here for simplicity. And alpha is just going to be whatever the index of the root, or whatever the index is of the node that we're currently looking at. So like if it was, but in the in-order array. So if we're looking at 3 here, the value for root would be 1 in the in-order array, and that's important to us. So because that's basically where the subtrees are split, right? It tells us how to split up those subtrees. So I'll just use this. So this is like the index of the, and I don't like root. It's just a node we're looking at. So I'll say node, but it's like the index of that node in the in-order array. So node, and that's going to be, but it's not just that. It's that plus that minus rather the index of the left marker, wherever that currently is in our in-order, or wherever it was last in our in-order array. So that's going to be the offset alpha, and then that's going to basically tell us, you know, where that left, or where the left subtree ends, right? So we'll take L here, and then we're just going to add alpha to L. And that's going to be how we know where how to divide apart these subtrees, right? So, and we'll walk through this a little bit just to kind of solidify this further. And then this for the right marker for the in-order is just going to be, it's more straightforward, right? It's whatever index that node was at minus 1, right? Since it's left, root, right, we just need to go to the 1 left to wherever that node was. And then for the right subtree, it's going to be very similar, but it's kind of like the opposite. So so for updating this left marker on the preorder array, we're just going to add alpha and plus 1. Okay, and then the again, it's pretty straightforward for the in-order array. We're just gonna take whatever index that node is at, and then just add 1 to it, 1 to the right of that. All right, so now that we have these rules, let's actually walk through this algorithm and build the tree from this. So let's get into this. So I'll just use a blue here. We know that the first node in preorder is going to be our root, so we'll start with that. We add a 3. Okay, now we need to basically add the left and right children, but the way we're going to do this recursively is we're going to add the left child first. Okay, but we don't know what it is yet, so we need to use these rules to help us. So so right now, our markers are going to start at the beginning and ends of both arrays, but the way we're going to update it for the left subtree is the left marker is going to be incremented by 1. So our new left marker will be here, and then our right marker is going to be left plus alpha. Now, and what is alpha? Alpha is going to be the index of the root, so this 3 here. So, and let's cross that out, by the way. So that's going to be 1 minus 1. So just, 1 minus 0. So that's just going to be 1. Because L was 0. So R is going to end up here, and that's going to be what we're looking at for the left subtree. And then for the preorder array, and then for the in-order array, L doesn't move, and then right, it's more straightforward, just goes 1 left of whatever that was. So we can see now that we're always going to build our tree nodes based on the value of the index of the left marker for the preorder array, because we know that's the root. So we can now add this node. We know it's going to be the 9, and then we're pretty much done with that. We're going to have basically a condition that's going to check when these overlap, and at that point we know we're at a null pointer, so we're just going to add null pointer and then pop back up from the recursion. So so these would overlap for both children, and we wouldn't go any further. So let's avoid doing all of that, save a little bit of time, and then we'll move down to the right subtree. So we basically pop back up. These are going to be, these markers are going to be basically, they're only going to have the scope of the recursive call, right? So so that they only really exist in this 9. When we pop back up, these are actually still going to be here and here, right, wherever they were before, and then you would update them like this for the right subtree, right? So the way they're going to get updated for the right subtree is, right, we said alpha was 1, so L is just going to increase by 2, which makes sense, right, because this 9 belongs to the left subtree. So the left marker is going to end up here, and we already added the 9, so let's cross that out too. So left marker is going to end up here, and then the right marker doesn't move, right, because we're dealing with the right subtree, and then The left marker for the inorder is obviously just, you know, the node we just added plus 1. So it's going to be like that. So pretty much identical, except these numbers are in a little bit of a different order. So we would add this 20, right? Because we're always going to use, again, that left marker, you know, whatever that is in the preorder array, because we know that's the root. So so 20 is can get added. And at that point, you know, we can cross out 20 because it's been added. Alpha at this point, let's see, let's keep track of this because we'll have to pop back up. So alpha is going to be, I'll just put this in parentheses, it's going to be node, which is, let's see, 0, 1, 2, index of 2 minus L, and L in both of these, or really just the L for preorder, is at this 2. So 0, 1, 2. So it's just going to be 0. Or actually, it's the index of node in inorder, so I made a mistake. So it will be 1 because 20 in this inorder array is 0, 1, 2, 3 minus 2, so that'll be 1. So alpha will be 1 there. Working on this left subtree, L is going to be L plus 1, and you know what? I'm going to use, I'm just going to draw, I'm going to leave these markers here because again, we need them for the, when we pop back up. So, but I'll just draw an additional marker basically for this left subtree recursion. So anyways, this left marker is going to be left plus 1, so it'll be here, and then we're going to add alpha to the left marker, and alpha is 1, so the right marker goes to here. So that's for our recursion. And then similarly for the inorder, left stays the same, and then right, you just subtract 1 from whatever the index is of that node. So we'd be here. So now we know that the left subtree is just going to be this 15. So let's get rid of that. And we can connect it finally. So that's going to be this 15. And then we would pop back up at that point, and now we've got to build the right subtree, right? So we're not concerned with where these markers are for the left subtree any longer because we pop back out. We can obviously see before we do anything that it's going to be the 7, but let's go through it just to be rigorous. So this the way this is going to update, we're going to use these rules on the right here. So the left is going to be alpha, which we said was 1 plus 1, so left plus 2, and that checks out, right? The right's not going to move. And then for the inorder, it's always easier, right? The left is just going to be 1 plus wherever that root node was, which is right there. So we've got that, and now we can see that this is going to be the right subtree. We can cross that out and add it to our tree. So 7, and that should be consistent with the answer. Let's go ahead and check. So 3, 9, 20, 15, 7, and looks exactly right. So that's pretty much just a step through the algorithm. It's just pretty simple recursion. These rules are a little tricky. I think the key here is being able to figure out how to map the use the inorder array to basically split up the preorder array and kind of use the two to, or basically use the position of the root in the inorder array to tell us how to split up our preorder array, how to move those markers, right? Because moving them around in the inorder array is a little easier. So anyways, the time and space complexity for this, we're going to have big O of in time, where in is the number of nodes or the number of elements in just one of the arrays, right? Or the number of nodes in the tree that we're building. That's how long it's going to take. And then for the space complexity, it's going to be big O of n plus h, because we're gonna need a hash map. So that's going to be linear with respect to n, because we need to be able to map basically the indices of these in order elements to their values. And then it's going to be h, because there's some space complexity for the recursive call stack when we're building our tree. So h is going to be the height of the tree. So big O of n plus h space. So yeah, let's just get into the code. So we're basically going to want, first thing is just that the hash map, right? So we'll use an unordered map for constant lookup time in C++. We just want integers, and I'll call it map. And then we're going to use a C-style for loop just to map those in-order values to their indices. That way we don't have to do a linear search every time we need one of those indices. So that's going to cut the time complexity down, even though the space is a little worse. It makes the time complexity much better. So in I0, right? And then we're going to say map is at in order I is just going to be equal to I, just to map those indices for constant retrieval time, constant access. And then we're going to write a recursive function separately. I'll just call it build. And we need that to return a tree node, right, to the recursively to the root of the tree it's building. And then we can just return root at the end of that. So let's start working on this recursive function now. So I'll make it a private function, or a private class method. That's going to return a tree node, and we're going to call it build. So it basically, as far as globals go, we need to know what the preorder array is. So we're going to need a vector of integers by reference, kind of for the quote unquote global preorder array. So we also need a vector of integers, same exact thing for the in order array. And then we also need to pass in that unordered map. So that's an unordered map where the key and the value are integers. By reference, of course. If we didn't do that by reference, we'd make a ton of copies, and it would be really computationally expensive, not good. So you want to use reference there for sure. Also, it wouldn't be modifying the same global data structures. The behavior would change entirely as well. So big difference here in recursion using reference and not using reference. So anyways, yeah, unordered map by reference. We also need those markers. So for the preorder left and right markers, I'll just call, those are going to be integers. And I'll just say PL for preorder left, P right for preorder right, and then same convention for in order. So IL and I right. Okay, so now that we have parameters down, let's go ahead and seed the function first here, because we didn't do that yet. So we're gonna need, we're gonna need, so basically both of these right markers, we can just take the size -1 once and not have to do that twice inside of that function call. So let's just do that up here. So we'll have an int, we'll call it last index is going to be preorder dot size -1 for that last index. Okay, and then we can pass in preorder, in order, the map. We want the 0 first, and then last index, and then 0, and last index again. Okay, so now let's start doing that recursion. So we first want to check if those markers have overlapped. So if P left is ever greater than P right, or I left is ever greater than I right, we can return a null pointer, because at that point we've reached leaf nodes, or we've gone underneath a leaf node, right? Or just a node that doesn't have both children, right? So we basically reached a null pointer, and we can pop back up from the recursion. So otherwise, we need to actually construct a tree node, right? So let's do, we're gonna need a new tree node, a pointer to a new tree node, and we're going to use the new keyword for the tree node struct, and then just pass in whatever the value is for the left marker in the preorder array, right? Because that's going to be the root. And then we can call our basically our recursion, right, on the children. So the way we're going to do that is we can say tree node's left child is equal to the recursive call of build on, you know, the correct parameters, which we'll get to. That's like the hard part. So, and then right on, we'll assign the right child to build with the corresponding parameters for the, you know, for the right child. So, and then after that, we can just return that tree node recursively. So yeah, so that looks good. Okay, so now we need to get these parameters. So easy parameters, preorder, inorder, and map. So let's go ahead and get those. I can literally just copy these because it's the same. But after that, it's going to be different, right? So let's go ahead and calculate. So we had some helper values, right? First of all, we need the root of, or the index of the root in the inorder array, right? So, and we created a hash map specifically for that purpose. So, so let's just create an integer called root index, I guess, or maybe we'll just call it root to be consistent with the whiteboarding. So this will be root, and it's really just the index of the root in the inorder array. So we're going to use map whatever preorder, because the current value we're looking at is the same one we just initialized that node with. So let me also put a space there because these lines are kind of unrelated. So so that's how we're going to get the index for the root there in the inorder array. Okay, and then we also need that value alpha, which I'll just call offset here. So call it offset, and it was the root minus the, I believe it was the index or the left marker on the inorder array, right? So it would be IL. Okay, so that's how we calculate the offset. Okay, and now the straightforward parts for this for the left subtree, for the left markers, we can just add 1. So preorder left plus 1 for the left marker. We're not going to worry about the right yet, and then the left marker for the inorder just stays the same for the left subtree, and then we're not going to worry about the right marker yet either, because that's the tricky part. Okay, and then we'll do the similar thing here. So not going to worry about the left quite yet, but we know the right doesn't change. And then same idea for the inorder array. Okay, so now let's work at the tricky part here. So the way we're going to update the offset for the right marker for the preorder array is we're just going to add that offset value to the somewhat counterintuitively to the left marker, right? Because we're trying to figure out where the left subtree ends, right? So it's going to be p left plus, so the preorder left marker plus the offset that we calculated. Okay, and then it's going to be kind of similar for the left value over here. So, but instead of just adding alpha, we also need to add 1. So it's going to be p left. So the marker for the left marker for the preorder array plus that offset alpha plus 1. Okay, and then for the in-order array, way more straightforward, right? So all we have to do is just take that root and then just subtract 1 from it, and then opposite for the right subtree, root plus 1 for that left marker on the in-order array. So that's pretty much it for the code. Let's go ahead and run this to make sure it works. Okay, so yeah, that about wraps up this video. So hopefully it helped you understand this problem more. If it did, leave a like and subscribe, and I'll see you guys in the next piece.